Many toasters, especially those with a metal exterior, do not have a ground conductor because they are considered double insulated. Double insulation means that the appliance has two layers of insulation between live electrical components and the user. This provides a high level of protection against electrical shock, even if one layer of insulation fails. In general, electrical appliances in the United States that operate at 120 volts alternating current and 15 amps or more are required to have a 3-wire power cord, which includes a ground conductor. This is because appliances of that size and power are more likely to cause an electrical shock if they develop a fault. However, there are exceptions to this rule. For example, appliances that are considered double insulated are not required to have a ground conductor, even if they exceed 15 amps. This is because the double insulation provides sufficient protection against electrical shock. The ground conductor provides an additional path for electrical current to flow in the event of a fault. This helps to prevent electrical shock by diverting the current away from the user. In addition, a ground conductor can help to protect against electrical fires by preventing the buildup of static electricity. Now let's delve deeper into the concept of double insulation. Double insulation, as mentioned, relies on two separate layers of insulation to protect users from electrical shock. Firstly, there's the basic insulation, which is the insulation on the wires themselves and the internal components. Secondly, there's supplementary insulation, which is an additional layer of insulation, often the appliance's outer casing, designed to prevent contact with live parts. This system ensures that even if the basic insulation fails, the supplementary insulation provides a backup, preventing dangerous voltage from reaching the user. The absence of a ground conductor in double insulated appliances doesn't compromise safety. The design inherently limits the risk of electrical shock, making a grounding wire redundant. Think of it as belts and suspenders. The double insulation serves as both, providing ample protection. Now consider the typical wiring configuration in a standard household circuit. It usually involves 3 wires: a hot wire, a neutral wire, and a ground wire. The hot wire carries the electrical current to the appliance, while the neutral wire provides a return path for the current. The ground wire, on the other hand, is a safety measure. It provides a low resistance path for current to flow back to the electrical panel in the event of a fault, such as a short circuit. This low resistance path causes the circuit breaker to trip, cutting off the power and preventing a potentially dangerous situation. However, in a double insulated appliance, the need for this ground wire is eliminated because the double insulation itself prevents the fault from occurring in the first place. The outer casing is designed to prevent any contact with live parts, so even if a short circuit were to occur internally, the user would not be exposed to the voltage. Moving on to the requirements for 3-wire power cords, the National Electrical Code, or NEC, plays a significant role in determining which appliances require them. The NEC is a widely adopted standard for safe electrical installation and wiring in the United States. It outlines the minimum requirements for electrical systems, including the types of wiring and grounding methods that are required for different types of appliances. As mentioned earlier, appliances that operate at 120 volts alternating current and 15 amps or more are generally required to have a 3-wire power cord. This is because these appliances draw a significant amount of power, and a fault in the appliance could result in a high level of current flowing through the user's body, potentially causing serious injury or even death. The 3-wire power cord provides a path for this current to flow back to the electrical panel, tripping the circuit breaker and preventing the electrical shock. However, the NEC also recognizes the concept of double insulation and allows for exceptions to this rule. Appliances that are designed with double insulation are not required to have a ground conductor, even if they exceed 15 amps. This is because the double insulation provides an equivalent level of protection against electrical shock. Furthermore, let's explore the benefits of having a ground conductor in appliances that are not double insulated. Firstly, it provides a low resistance path for fault current to flow back to the electrical panel. This is crucial because it allows the circuit breaker to trip quickly, cutting off the power to the appliance and preventing an electrical shock. Without a ground conductor, The fault current may flow through the user's body, resulting in a potentially fatal electrical shock. Secondly, a ground conductor can help to prevent electrical fires. Electrical fires can occur when there is a buildup of static electricity in an appliance. Static electricity can be generated by friction between moving parts or by the flow of electricity through the appliance. If the static electricity is not properly discharged, it can build up to a high voltage and eventually arc to a nearby grounded object, such as a metal pipe or a person. This arc can ignite flammable materials, such as dust or fabric, causing a fire. A ground conductor provides a path for the static electricity to discharge safely, preventing the buildup of voltage and reducing the risk of fire. Thirdly, a ground conductor can help to protect sensitive electronic components from damage. Electronic components are susceptible to damage from voltage surges, which are sudden increases in voltage that can occur due to lightning strikes or other electrical disturbances. A ground conductor can help to divert these voltage surges away from the electronic components, protecting them from damage. In summary, the presence or absence of a ground conductor in an appliance depends on several factors, including the appliance's design, its power consumption, and the applicable electrical codes. Double-insulated appliances are designed to provide a high level of protection against electrical shock without the need for a ground conductor, while other appliances may require a ground conductor to ensure safety. Always follow the manufacturer's instructions and local electrical codes when using electrical appliances to prevent electrical shock and fire hazards. Now, let's consider some specific examples of appliances that may or may not have a ground conductor. Firstly, many small kitchen appliances such as blenders, food processors, and electric kettles are double insulated and do not require a ground conductor. These appliances typically have plastic housings and are designed to prevent contact with live parts. Secondly, some larger appliances such as washing machines, dryers, and refrigerators are not double insulated and require a 3-wire power cord with a ground conductor. These appliances typically have metal housings and are more likely to cause an electrical shock if they develop a fault. Thirdly, power tools such as drills, saws, and sanders may be either double insulated or require a ground conductor, depending on their design. Double insulated power tools typically have plastic housings and are marked with a symbol indicating that they are double insulated. Power tools that are not double insulated require a 3-wire power cord with a ground conductor. Understanding the difference between double insulated appliances and those that require a ground conductor is crucial for electrical safety. Always check the appliance's label or the manufacturer's instructions to determine whether it is double insulated or requires a ground conductor. If you are unsure, consult a qualified electrician. Additionally, it's important to note that even if an appliance is double insulated, it is still important to use it safely. Avoid using appliances in wet or damp conditions, and always unplug appliances when they are not in use. Inspect power cords regularly for damage, and replace them if they are frayed or cracked. By following these safety precautions, you can minimize the risk of electrical shock and fire hazards. Let's delve further into the specific requirements outlined by the National Electrical Code, or NEC, regarding grounding and bonding. The NEC provides comprehensive guidelines for ensuring electrical safety in buildings and electrical systems. Article 250 of the NEC is dedicated to grounding and bonding, and it covers a wide range of topics, including the types of grounding systems, the size of grounding conductors, and the methods of grounding equipment. According to the NEC, all electrical equipment that is likely to become energized must be grounded. This includes metal enclosures, motor frames, and other conductive parts that could come into contact with live electrical conductors. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protective device, such as a circuit breaker or fuse, and to energize the circuit. The NEC also requires that all grounding conductors be properly sized to carry the maximum fault current that could occur in the circuit. The size of the grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. For example, A 20-amp circuit breaker requires a minimum 12 American wire gauge copper grounding conductor according to NEC Table 250.122. In addition to grounding, the NEC also requires bonding of all metal parts that are likely to become energized. Bonding is the process of connecting metal parts together to create an electrically conductive path. This ensures that all metal parts are at the same electrical potential, which helps to prevent electrical shock hazards. The NEC specifies the methods of bonding equipment, including the use of bonding jumpers, bonding screws, and other approved bonding devices. It's important to note that grounding and bonding are two distinct but related concepts. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts are at the same electrical potential. Both grounding and bonding are essential for electrical safety. Now, let's consider some common grounding and bonding mistakes that can lead to electrical hazards. Firstly, failing to properly ground equipment is a common mistake. This can occur where equipment is installed without a grounding conductor or when the grounding conductor is not properly connected. Secondly, using an undersized grounding conductor is another common mistake. This can occur when the grounding conductor is not sized according to the NEC requirements. Thirdly, failing to properly bond equipment is a common mistake. This can occur when bonding jumpers are not installed or when bonding screws are not tightened properly. Fourthly, using dissimilar metals in grounding and bonding connections can lead to corrosion and poor electrical contact. This can occur when copper grounding conductors are connected to aluminum enclosures without using a listed bimetallic connector. Avoiding these common grounding and bonding mistakes is crucial for electrical safety. Always follow the NEC requirements and the manufacturer's instructions when installing and maintaining electrical equipment. If you are unsure about any aspect of grounding or bonding, consult a qualified electrician. Let's further clarify the distinction between grounding and bonding with some practical examples. Imagine a metal electrical enclosure that houses circuit breakers. Grounding this enclosure involves connecting it to the earth through a grounding electrode conductor, which is typically a copper wire connected to a ground rod or a metallic water pipe buried in the ground. This connection provides a lower impedance path for fault current to flow back to the source, which helps to trip the circuit breaker and energize the circuit in the event of a fault. Now, imagine that there are several metal conduits connected to the electrical enclosure. Bonding these conduits involves connecting them together with bonding jumpers, which are short lengths of copper wire. This ensures that all of the metal conduits are at the same electrical potential, which helps to prevent electrical shock hazards if someone were to touch two different conduits at the same time. Another example is a metal water pipe that runs through a building. Bonding this water pipe involves connecting it to the electrical grounding system with a bonding jumper. This helps to prevent the water pipe from becoming energized in the event of a fault, which could create an electrical shock hazard if someone were to touch the pipe while it was energized. In each of these examples, grounding provides a path for fault current to flow back to the source, while bonding ensures that all metal parts are at the same electrical potential. Both grounding and bonding are essential for electrical safety and are required by the NEC. Additionally, it's important to understand the role of ground fault circuit interrupters, or GFCIs, in electrical safety. A GFCI is a device that is designed to protect people from electrical shock by monitoring the current flowing in a circuit. If the GFCI detects a difference in current between the hot and neutral wires, it assumes that some of the current is leaking to ground and it quickly trips the circuit, cutting off the power and preventing an electrical shock. GFCIs are typically installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires GFCIs to be installed in all new construction and renovations in these areas. GFCIs are an important safety device that can help to prevent electrical shock injuries and fatalities. However, it's important to note that GFCIs are not a substitute for proper grounding and bonding. GFCIs are designed to protect people from electrical shock, but they do not prevent electrical fires or protect equipment from damage. Grounding and bonding are still essential for providing a safe and reliable electrical system. In summary, understanding the concepts of grounding, bonding, and GFCIs is crucial for electrical safety. Always follow the NEC requirements and the manufacturer's instructions when installing and maintaining electrical equipment. If you are unsure about any aspect of electrical safety, consult a qualified electrician. Let's consider some troubleshooting tips for electrical grounding problems. Firstly, if you suspect that there is a grounding problem, the first step is to check the grounding connections. Make sure that all grounding conductors are properly connected to the equipment and to the grounding electrode system. Secondly, use a multimeter to test the continuity of the grounding conductors. A multimeter is a device that can measure voltage, current, and resistance. To test the continuity of a grounding conductor, set the multimeter to the continuity setting and connect the probes to the grounding conductor at 2 different points. If the multimeter shows a low resistance reading, then the grounding conductor is continuous. If the multimeter shows a high resistance reading, then there is a break in the grounding conductor. Thirdly, check the grounding electrode system. Make sure that the grounding electrode system is properly installed and that it is in good condition. The grounding electrode system typically consists of a ground rod or a metallic water pipe buried in the ground. Fourthly, if you are experiencing frequent tripping of circuit breakers, it could be a sign of a grounding problem. Check the grounding connections and the grounding electrode system to make sure that they are properly installed and in good condition. Fifthly, if you are experiencing electrical shock, immediately turn off the power to the circuit and call a qualified electrician. Electrical shock can be a sign of a serious grounding problem. Troubleshooting electrical grounding problems can be dangerous. If you are not comfortable working with electricity, consult a qualified electrician. Let's also discuss surge protection devices and their role in protecting electrical equipment. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, which are sudden increases in voltage that can occur due to lightning strikes or other electrical disturbances. Voltage surges can damage sensitive electronic components, such as computers, televisions, and appliances. SPD work by diverting the surge voltage away from the equipment and to ground. SPD are typically installed at the service entrance of a building, but they can also be installed at individual circuits or appliances. There are 2 main types of SPD, Type 1 SPD and Type 2 SPD. Type 1 SPD are installed at the service entrance of a building and are designed to protect the entire electrical system from voltage surges. Type 2 SPD are installed at individual circuits or appliances and are designed to protect specific equipment from voltage surges. The NEC requires SPD to be installed in certain applications, such as in dwelling units and in critical facilities, such as hospitals and data centers. SPD are an important part of a comprehensive electrical protection system. However, it's important to note that SPD are not a substitute for proper grounding and bonding. Grounding and bonding are still essential for providing a safe and reliable electrical system. In summary, understanding the concepts of surge protection, grounding, and bonding is crucial for electrical safety. Always follow the NEC requirements and the manufacturer's instructions when installing and maintaining electrical equipment. If you are unsure about any aspect of electrical safety, consult a qualified electrician. Now, let's examine the role of isolation transformers in electrical safety. Isolation transformers are used to isolate electrical equipment from the power supply. This isolation helps to prevent electrical shock hazards and to protect sensitive equipment from damage. Isolation transformers work by providing a separate electrical path for the equipment, which is not connected to the power supply ground. This isolation prevents any fault current from flowing through the equipment and to ground, which could cause an electrical shock. Isolation transformers are typically used in medical facilities, industrial plants, and other areas where there is a high risk of electrical shock. The NEC requires isolation transformers to be installed in certain applications, such as in patient care areas of hospitals. Isolation transformers are an important safety device that can help to prevent electrical shock injuries and fatalities. However, it's important to note that isolation transformers are not a substitute for proper grounding and bonding. Grounding and bonding are still essential for providing a safe and reliable electrical system. In summary, Understanding the concepts of isolation transformers, grounding, and bonding is crucial for electrical safety. Always follow the NEC requirements and the manufacturer's instructions when installing and maintaining electrical equipment. If you are unsure about any aspect of electrical safety, consult a qualified electrician. Let's now consider the topic of electrical safety audits and their importance in maintaining a safe electrical system. An electrical safety audit is a comprehensive inspection of an electrical system to identify potential hazards and to ensure that the system is in compliance with the NEC and other applicable codes. Electrical safety audits are typically conducted by qualified electricians or electrical engineers. The audit includes a visual inspection of the electrical system, as well as testing of the grounding and bonding connections, the overcurrent protective devices, and other electrical components. The audit report provides a list of any identified hazards and recommendations for corrective action. Electrical safety audits are important for identifying potential hazards before they can cause an accident. They can also help to ensure that the electrical system is operating safely and efficiently. The frequency of electrical safety audits depends on the type of facility and the complexity of the electrical system. However, it is generally recommended that electrical safety audits be conducted at least once every 3 years. Electrical safety audits are an important part of a comprehensive electrical safety program. By conducting regular electrical safety audits, you can help to protect your employees, your customers, and your property from electrical hazards. In addition, it's important to emphasize the importance of lockout-tagout procedures for electrical safety. Lockout-tagout, or LOTO, is a safety procedure that is used to prevent accidental energization of electrical equipment during maintenance or repair. LOTO involves isolating the electrical equipment from the power supply and then placing a lock and a tag on the disconnect switch to prevent it from being turned on. The lock and tag must be removed by the person who performed the maintenance or repair. LOTO is an important safety procedure that can help to prevent electrical shock injuries and fatalities. The Occupational Safety and Health Administration, or OSHA, requires employers to implement LOTO procedures for all electrical equipment. Implementing LOTO procedures requires training employees on the proper procedures and providing them with the necessary equipment, such as locks, tags, and disconnect switches. LOTO is an essential element of a comprehensive electrical safety program. By following LOTO procedures, you can help to protect your employees from electrical hazards. In conclusion, always prioritize electrical safety and take the necessary precautions to prevent electrical accidents. If you are not comfortable working with electricity, consult a qualified electrician.